So now this is my great pleasure to introduce our next speaker. This is the official winter school part of it. It's a lecture 1. The title is Optical Engineering, a key enabler for technology in daily life. And the lecturer will be Professor Yuzuru Takashima. And I am sure we will learn a lot from him. Yuzuru, thank you. The stage is all yours.
Okay, thanks, David. Can you guys hear me?
Yes, we are looking at your presentation view.
Right.
Would you switch your screen?
Yes.
Going to display setting? Yes.
Yeah, let's see. Where can I go? So display.
Oh, I think you need to go up to the display setting.
Oh, yeah. Hold on.
You, top of the screen, you see display setting right now, right?
Yeah, it's actually behind the menu bar.
Yes, right there. Click there.
Okay, display. All right, wonderful. Swap.
That's exactly what you need to do.
Okay. So can you guys hear me?
Yes, now we have your full screen, and thank you. Please begin.
Wonderful. All right. Yeah, thanks for introduction, and welcome to our Winter School 2022. And I'm Yuzuru Takashima, Associate Professor here at UArizona Optical Sciences. So then today I'm gonna talk about optical engineering as a key enabler for technology in daily life. So Tom, as well as Hong, actually gave a great talk on technologies in daily life, but I will actually entertain and recap a little bit about those again. So as you can see here, so we have a bunch of technologies in our daily life. So cell phones, cell phones and cameras, and also so this is a cloud, right? Communications, and of course streaming. Everything is there, of course, with computer. So then today I will actually convince you guys optics as well as optical engineering is a key enabler for those technologies in daily life. Okay, so this is our objective today. So then before starting this talk, I'd like to actually go back a little bit of history. So long time ago, so you guys usually say Spotify, Apple streaming, Amazon streaming music or video, right? So there's a very important event back to 1979 at Philips Research Center in Eindhoven, Netherlands. So can you guys think of anything? So this actually is before you guys born. So this is actually a compact disc, CD. So amazingly, so this compact disc, this is an optical disc, has over 50 years of history. And this compact disc at the left shows the first mass-produced compact disc from Philips. And on right, so he's a pianist, I think Claudio Allau, and he recorded Chopin's waltz. So this is the first mass-produced compact disc, so back in 1982. And as an interesting story, so this Claudio Allau actually push button of a CD stamper, and he actually is the first guy to push the button of a mass production facility for CD discs. So on right, you see a old gadget, CD drive prototype. So back to 1970. So now how it works. Well, so this is basically optical devices, so combined with laser and detector and lenses and electronics and actuators and such. So as you can see from a middle, so scanning electron micrograph of image of disk. So there are very tiny bulbs, so-called beads, are stamped on disk And the laser actually tracks those small bits. As you can see from here, so lengths of tiny bits are actually encoded such that, so this information records 74 minutes digital audio. So for example, now on right, you see Herbert von Karajan. So he's a famous conductor from Berlin Fair. And so on right, so Akio Morita, so he was president of Sony. And so these guys talked together. So how long this CD disc has to record? Then Karajan said, hey, I want to record a symphony number 1 Beethoven. So it requires 74 minutes. So this was how the specifications of CD drive was determined. So this is a very interesting story, but as we know, so this technology is kind of diminishing, especially for consumer applications such as music and video and such. But still, so there's a demand for this kind of storage devices. So now we need a big cloud storage system. So this triangle shows hierarchy of data. So then width shows capacity, and color-coded triangle shows a speed, I say. So then there are two different kinds of data, so-called hard data and cold data. So cold data is a data which is not accessed so often, but it has to be stored for a long time, so for archivable applications. So as compared to a cold data, so there's a so-called hot data. So this is frequently accessed data, such as video and music and such. So based on this data hierarchy, so different kinds of storage technologies were developed and applied in so-called, for example, in hot data, flash memory SSD, and cold data, tape, as well as optical drives. So then we don't use optical drives anymore for streaming, but still, so optical technology takes an important role for a long time archivable applications for cold data. So as you can see from here. So there are other optical technologies used for archivable storages, such as holographic data storage. Also, amazingly, HDD hard disk drive uses optics, as we can discuss a little bit later. So then let me show you very interesting technology, so which is holographic data storage. And I found one very interesting video. I will actually share this video with you. So hold on, so I guess I need to stop share once and share again. So while enabling sound, okay.
So how does holographic data storage work? In order to record a hologram, we encode data into a 2D image using a spatial light modulator. This is very similar to a cell phone screen. We then combine that beam with a reference beam inside the lithium niobate crystal, and the data is encoded as the interference pattern. We can record multiple beams simply by changing the angle of this reference beam using a MEMS mirror. That allows us to record many data sets in the same volume. To read out the data, we simply use a reference beam at an angle designed to select the page we want, and that recreates the original data page which we capture on a camera. We can read out different pages simply by changing the angle of this reference beam. The great thing about holographic storage is we can then move to other locations in the crystal to write more data. The crystal can be completely erased using UV light and then reused indefinitely to store more data.
Okay, so you might notice that. So this video was generated by Microsoft. And this is very interesting to me because now, so those guys are again re-evaluating, redoing research on this holographic data storage. And so this technology actually is very, very old. So now I actually cited two papers. The oldest one is from J. Van Heeden. So a new optical method of storing and retrieving information. And as you can see from here, so this is April 1963. And it's already 60 years ago. So once this idea was invented. So then again, people are looking, this technology again now, 2020, so including Microsoft and other people. So, so this holographic data storage, unfortunately, so didn't go well. So there are a couple of, or many reasons. So you see once you start a program at OSC and you can learn and understand. So the other interesting storage technology is, of course, hard disk drive. And the hard disk drive is a magnetic device, but interestingly and amazingly, so optics also are involved there. So I also found a very interesting video from Seagate. So let me share this video with you.
So where we are today with what we call perpendicular magnetic recording, the magnetization points perpendicular to the surface of the disk. So you can think of it as little magnets pointing up and down. That represents the data that you want to store on the disk. At some point, these little magnets become unstable. Just from the thermal energy around the room, they can actually flip. So what we had to do with heat-assisted magnetic recording, or HAMR, is come up with a whole new recording material that's very, very hard to flip. So what we've had to do is add some extra energy into the system, and the energy that we're adding is heat. In HAMR, we couple a laser light into the recording head, focus that laser light down to very small spots, and that heats up the media to a point where it's easier to flip the magnetization. So we're heating up the recording material to 450 degrees C, and then cooling it back down to room temperature all in a nanosecond. Makes it a lot of fun from an engineer's point of view.
Yeah, so would that be very interesting? Now, so magnetic recording takes advantage of optics. And, this technology has been researched over a decade or 2 decades. So this paper shows, how this system works. So on left, so explains, how a magnetic flux alters data bit, so which is actually pole of a tiny, tiny magnet data bits. And on the middle panel shows how laser is actually introduced in this magnetic head. You see, red laser illuminates some grating structure, and the grating converts free space light into like a guided light. And finally, so that guided light, you see on right, very small lollipop type of antenna. So the size of antenna is about tens of nanometers, very, very small. So this antenna finally converts this propagating light into a evanescent light, which actually heats up locally and very, very tiny tiny area of magnetic recording media. So optics is actually involved in this hard disk drive too. So what's next? Now, Professor Honghua actually gave a very interesting talk, and of course, the technology daily life so includes VR and AR displays. Okay, so I don't explain too much about this again because now Professor Hua explained very, very well. So, but let me again review a little bit of history. So we use AR goggle or VR goggle, right? But on bottom right, you see, example of classical 3D goggle. So the, form factor and shape is pretty much similar to what the state of the art. So now Google Cardboard-based VR display uses cell phone, and of course we have more advanced devices such as Oculus Quest. So there's a history. So how about optics? So as you can see from here, so this VR device is basically a magnifier, okay, magnifier. And the magnifier is made out of lenses. But people use this so-called Fresnel lens, very thin lens. So even people use this so-called pancake lenses, polarization-based optical design. So that enables very high, large FOV field of view, so as well as very high resolution. So how those look like? So on left, so this is a Fresnel lens. You see a bunch of concentric lines. So that actually adds additional function on this lens. So which makes a very thin and lightweight, so which is made out of plastic. So on right, so this is actually pancake, not the lens, but you see two stacked components in this figure, right? And if you look into how ray propagates through this pancake, you see, so ray actually goes twice inside this pancake structure. Yeah, so then people have a very clever trick. So this is taken from one of the patent applications. So you see, so light goes back and forth, so between optics and while taking advantage of polarization. So which is, I think, is very interesting design. So in terms of improving performance, such as field of view and resolution, so while making very, very compact lens like we see now. So other displays. You guys watched the movie, Star Wars. So this is a classic movie. And in Star Wars, there's a very, very famous scene, so those guys look into 3D projected image of Princess Leia. Yeah, and so people are dreaming for a long time. So how can we make that? So now there are many, many challenges, and still the effort are going on. So one interesting, relatively straightforward approach is on bottom. You see, so this is a virtual character, Miku, and you see, many audiences in front of Miku is actually watching her. But of course, this is not the real Miku, but it's a projected image. And if you look into carefully, so there's a screen, and so there's a reflection from audiences on the screen. And so there's a blind spot on the image of Miku, right? So this is actually a projected image. So projector is placed behind the screen, so it is semi-transparent. And the Miku is actually making a performance. So another device, so this is so-called HoloLens from Microsoft. So then there's a little bit of confusion. So this is not a holographic display, but certainly holographic optics are in there. I took this image from a website and see how a device's component inside HoloLens look like. And you see on a bottom left, so there's a transparent device. So this is so-called holographic combiner, so which combines a projected image with see-through image. So how it works? Well, so we have a transparent glass plate. And so there's a diffractive structure, tiny groove patterns, which is fabricated on that transparent piece of glass. And that actually couples image information from microdisplay, so with external view. So but you can think of this now. So this is actually camera finder, as you can see from right. So we see classical Leica M3, so which is back to 1950. And if you look into Finder, so there's a combination of information. So one is a outside image, and so second one is Finder frame. Basically, this optics for AR is we can consider as a modern Finder optics of camera system. Okay, how about more radical solution? So display by contact lens. Why don't we just implement a function on contact lens? So certainly, many people are interested in this kind of approach. So on left is contact lens telescope, and so that actually combines a see-through view with telescopic view. And on left bottom, so there's a picture of that contact lens. This looks a bit scary for me, like a sci-fi take, but that's very interesting. And of course, other people are interested in implementing display, so LED array directly on top of contact lens. And on right, so this is one of the demonstration back to 2013 by University of Washington. So they actually incorporated LED, and which is actually powered by antenna. And so that was tested by using, I think this is a rabbit or something like that. You see, the LED actually is blinking. So this is remotely activated LED, so which is implemented on contact lens. Okay, so how about this? Now, so AR VR is also is actually a very big market, but in these days, optics in mobility, so autonomous driving, so such as a display and LiDAR sensors. So then there are huge demand for this kind of devices too. And as you can see, driver is reading book while driving. I don't recommend it. So this is dangerous. But you see, the self-driving, the information is displayed on the windshield, and sensor like a LiDAR sensors, so detects a car which is in front of this car. So this is also a very hot topic in optical engineering. So how LiDAR optics look like? Well, so LiDAR is basically laser transmitter and receiver. Okay, combination laser transmitter and receiver. So from top left, so we have a laser diode, and followed by different filter substrate, which actually blocks light from ambient and protect the windows and thin film coating and such. And of course, so there's some actuator, so-called MEMS, microelectromechanical mirrors, which steer beam for transmitting light. And so detectors and optics are involved there. So then those of you guys who may actually notice that this is pretty similar to historical compact disc drive, right? So these are optics and actuators and detectors. So I know you guys know this guy, Elon. So he doesn't like LiDAR. Okay, so Elon Musk calls LiDAR stupid, but most self-driving cars use it. He was right. And Elon is even telling freaking stupid. Why? Yeah, so but in reality, there's another prediction. So this shows how LiDAR sensors will be adapted over the decades. So some study shows in 2030. So we expect that about 20 million units of LiDAR will be incorporated for especially advanced driver assistance systems, so-called ADAS. And on right, in this car, you see a bunch of sensors incorporated. And most likely, multiple LiDAR sensors will be installed in cars. So which, for example, senses a very far object, 300 meters from car, as well as a recognition of surrounding environment, so close to that car, say over the range of 10, 20 meters. So how LiDAR system works? Well, so this is so-called a time of flight measurement. So LiDAR is actually made out of transmitter, illumination source with laser, and detector. And so there's a stopwatch. So once a laser pulse is launched from illumination source, stopwatch starts, and light actually reflected back from object to detector. So then, stopwatch actually stops. So then if we measure time, so which is t, and we know speed of light, and we can back calculate so distance d, so by measuring so-called time of flight. So this is so-called TOF LiDAR. There are other ways to measure distance, like a frequency modulated continuous wave LiDAR, but so this is the most simplest way to do. Okay, so what's the fundamental limitations, which is speed of light. So then I compared how many data we can grab by using camera, so as compared to a single point scanning LiDAR system. For example, cell phone camera captures 12 megapixels of images, so over 10 times per second, so 10 frames per second. So which actually has a data capture rate of 120 megapixels per second. So in contrast, so LiDAR uses time of flight, speed of light. So then suppose we measure an object at 300 meters away from car, so which is 600 meters of round trip. So it takes about 2 microseconds. So then if we limit ourselves, just use single detector, so data rate is only 0.5 megapixels per second. So that actually sees the difference of the images between LiDAR image and camera images. So in that sense, Elon is, I think, in some sense right, but at the same time, so this is a huge opportunity for us, optical engineers, optical scientists. How can we boost up this data rate for LiDAR system? I think this is a very, very interesting challenge for us, including you guys. So the other aspect is, of course, safety. So the other fundamental limitations is, amount of light, so limited by eye safety. So then LiDAR uses infrared, mostly 905 nanometer for TOF measurement, and 1550 nanometer for other cases, such as FMCW, of course, TOF. Then human eye absorbs, say, 1550 nanometer infrared light. So therefore, it is believed to be safe, as compared to 9405 nanometer TOF LiDAR. So then this is the reason why, so if you look into right, so the long range LiDAR needs a bigger optics. So why? Bigger optics allows us to use a weaker laser pulse, so which is more eye safe, so especially for 905 nanometer. Yeah, so this is also very interesting optical engineering challenge. So, but is 1550 really safe? This is another interesting article I found. Now, as you can see from here, Man says CES consumer electric show LiDAR's laser was so powerful, it wrecked his 2000 bucks camera. So this is a story. I think this was 2 or 3 years ago. One guy who was using a camera captured image of a LiDAR or car with LiDAR, and as you can see from a left, and sometime later, so he took a picture of on right, and so he found that, or he or she found that, so there's a bright 2 artifacts there. Yeah, so this is kind of a typical artifact. So once a detector pixel, CMOS pixel, is damaged. So this, laser is actually 1550, not 905. But, actually, so it looks like now, so pixel is damaged by this laser rangefinder LiDAR system. So why that happens? Well, so if we compare, pupil size of eye as compared to, pupil diameter of a camera, so there is a huge difference, about 18 times of difference. So which actually is, 324 times or maybe more power density at detector. So now I think so this is possible. So having a large pupil area. So now maybe most likely so detector was damaged by 1550. So this is also very interesting challenge, right? So we expect that 2030, so about 20 millions of LiDAR sensors will be equipped in the car. And they think about that. We have many cars, so at the intersection point, okay, and the scanning laser beam, and in 360 degrees. So this actually is a LiDAR laser war, as you can see from right? So we are shooting lasers, between cars, between people, and that's a very interesting also problem we can think of. How can we solve, or how can we effectively, detect object by using LiDAR without making this kind of chaotic situation? Okay. So a little bit of in detail, laser beam steering is essential and also very important, research area in optical engineering. Many different companies are doing different ways, spinning mechanical scanning and spinning mechanical scanning and frequency spectrum scan, optical phase array, micromotion, and such. Yeah, so then as we understand that, we need to steer beam in a very wide angle with high resolution very fast. And so we research a very interesting way to steer beam by using so-called a micro electromechanical system based display device, MEMS display device. So as you can see from here, so we have a device which is commercially available. So digital micromirror device, DMD. And on right, you see a bunch of small mirrors are tiled. The size of this small mirror is about tens of microns. And this micromirror works as a grating, and we can steer beam by applying principle of grating. So this is a little bit about what I meant. You see that in Thursday lab tour. So we study LiDAR system by using a digital micromirror device, and which actually makes a scanning object without moving part and with high resolution and wide field of view. So we steer beam, but we can also steer image. So in the next slide, so this will be also on Thursday lab tour. So by using same device, so digital micromirror device, so we steer not only beam, but image. So why it's important? Professor Hongfu actually raised challenges in air display. So we need a very large FOV and high resolution, so which requires many numbers of pixels. So, but by steering images or foveation, so we can actually use less number of pixels and while producing required amount of information. So wide field of view with high resolution. So now this is one of the demonstration of gigapixel image steering for AR foveated display by using megapixel display. Okay, so then let me again go back to history of compact disc. Now, compact disc development had started back in 1970 and 1982. So this was a first compact disc player, so which is commercially released compact disc player. So in 1982. So the list price was $730. So, but over a couple of decades of development and cost reduction and R&D. So now at the end of history of CD drive, the disk drive, core part of disk drive, which is the optical pickup head, costs just less than $10. So where we are right now in LiDAR and AR/VR device history, so I think it's very early. So around 1970 or 1982, something like that, right? So now this actually is indeed a great opportunity for us as optical engineer scientist or optical engineering student. So we have plenty of things to do towards a very compact and lightweight and low cost and mass-produced a product of LiDAR and AR/VR systems. Okay, hope I convinced you guys. So optical engineering is a key enabler for technology in daily life. So then, so this is a list of our optical engineering faculties, and including myself. So then I hope you found this optical engineering is a very interesting and promising discipline in optics, and hope you join us and do great research together. Okay, thank you very much for your attention. Then if you guys have any questions, I'd be happy to answer for your question.
Thank you very much, Yuzuru. This is a very nice summary and really telling the story and history of optical engineering, how it has been affecting our daily life truly and enabled many things as we are living this awesome world today. We have a few interesting questions in the chat box, but I will let the student actually ask the questions with their voice. That will be more exciting. So let's have some Q&A session. We have about 10 minutes. This is exciting. Kevin, I saw you are asking a very nice question in the chat box. Would you repeat your question and Yuzuru may answer? Kevin-san?
Yes. So my question was that do weather conditions such as humidity, precipitation, temperature have a significant impact on the accuracy of LiDAR imaging? And also, I was wondering, in real world situations, do LiDAR emitters on different autonomous vehicles interfere with each other? And if so, is that a significant, how do we solve this problem, I guess?
Yeah, okay, yeah, that's a great question, Kevin. Yeah, so first question is now, how environment affects on a detection of LiDAR system, right? So then it does affect, for example, under fog or rain condition, the signal is strongly attenuated, right? So that actually decreases the range, detection range. So there is also research which actually mitigates the effect of those turbulences. So there's optical engineering research areas which is focusing on detecting something behind a scattering media or even unseen object. So then my perspective is now, eventually, so LiDAR research going to actually use those techniques to mitigate the effect of rain and fog and such. So did I answer my question for the first one?
Yeah.
Yeah.
Thank you.
So the second one was, excuse me, for one question. Sorry, would you repeat it again? Second question was?
Yeah. My second question was that in a real world situation, like this.
Interference.
Yes.
Right. Yeah. Okay. Yeah, you can think about this. This is a communication problem, right? So we have a transmitter and receiver. So we only want to communicate, by ourselves, between me and me, between you and me, right? So that's the interference. So then there is a so-called technique to encode information so that encoded information doesn't interfere with each other. Yeah. So then there certainly is a way to pick up signal from our own transmitter only. So while rejecting interference from other LiDARs, so-called alien LiDARs. Yeah, so this is also a very hot topic in LiDAR research.
Thank you.
James, you also have a next question, extending Kevin's question. Would you ask?
Yeah, absolutely. So this is sort of building off of Kevin's question, but I live in a region where if it's very snowy and very windy, it can be almost impossible to see outside, even with the human eye. So I was wondering if that presents additional challenges to LiDAR systems being able to detect,
Yeah, definitely. Yeah, right. Yeah, question is now, LiDAR is not only a solution, right? Like Elon Musk is claiming. So most likely, we have to combine, different sensing modalities like radar, so millimeter wave radar, and camera, and LiDAR, even ultrasonic. So then, those data has to be fusion, right? So then to sense environment, but not just only by LiDAR, but all the sensors working together. I think this is also a very interesting aspect of this, research for autonomous sensing. Did I answer the question?
Yes, thank you.
Thank you very much. Anyone else has any other questions? So Yuzuru, I have just one overview question. So
Sure.
you represented the optical engineering field
Yep.
Among big optical sciences, right? So could you just give some overview about what topics are included in optical engineering field? So for instance, what classes?
Oh, classes. Yeah.
Or
Let's
what
see.
topics in general?
Yeah, so then I can go over, this picture, right? So from top left, Ron Drigger. So he's an expert of infrared imaging, followed by John Riebenkamp. So he is teaching geometrical optics, very fast order optics, and on Hua, we know what he's doing. And Deu, so he's an expert of metrology, interferometry and measurement of big mirrors. And Ron Dian, so he's working on biomedical optics as well as lens designs. And Tom Milster, so he has a diverse research portfolio, so ranging from diffractive optics to space optics. And on bottom left, Jose Sachian, so he's a go of lens design, and followed by Jim Spielring. And he's focusing on eye optics, and me, so I'm focusing on LiDAR and displays. And we have a new faculty, Travis. So he actually is a graduate from optical science, and he started working on biomedical optics. And we have a new guy, so named Brandon. So he's working on X-ray optics. And also finally, also Chickman, so he's an expert in polarization. Yeah, so we have a diverse portfolio in optical engineering. So did I answer for the question, Dave?
Thank you very much, Yuzuru. That was a great lecture, and we appreciate it.